Thank you for the introduction. So the purpose of our experiment was to determine how acoustic radiation forces and/or endogenous cavitation from pulse focus ultrasound alter the tissue microenvironment. So to start off with some background, our lab has shown that when you target pulse focus ultrasound to kidney or skeletal muscle, you are able to induce an increased mesenchymal stem cell homing response in these tissues for a therapeutic effect. Looking further at this mechanism, we have found that pulse focus ultrasound mechanically activates TRPC1, resulting in calcium-dependent COX-2 increase in expression via NF-kappa B, which results in an increase in PGE2 production and downstream cytokine, chemokine, and trophic factor and cell adhesion molecule upregulation, which results in the mesenchymal stem cell homing response. At pulse focus ultrasound treatment parameters we've been using, you're able to observe both acoustic radiation forces and endogenous cavitation. So my project sought to understand how these two forces interact to contribute to the downstream molecular response. So how we designed the experiment is that we treated NIH Swiss mice hamstring with either a 0.5 or 1.12 megahertz transducer at one of a range of treatment pressures. There were no microbubbles used in this experiment. 6 hours after treatment, we harvested the muscle tissue and performed PGE2 quantification. We also used real-time monitoring by hydrophone to look at the emission spectra. And we then analyzed for harmonic emissions as a measure of stable cavitation and interharmonic noise as a measure of inertial cavitation, and both were background corrected. As you can see on the right, this is an example spectra for looking at harmonics and interharmonic noise, where treated is shown in blue and the background is shown in red. So here I'm showing a full PGE2 increase, and it is normalized by control untreated hamstring. We also show where we can see the detection of harmonic and broadband emission for each frequency transducer. The first thing I'd like to point out is that we are able to see a significant PGE2 increase at a peak negative pressure below that which we can detect harmonic emissions. When we fit a curve to these different transducers, we were also able to compare the two curves to determine whether they're significantly different using the extra sum of the squares F-test. And as you can see here, they are significantly different. And this means that PGE2, when related to peak negative pressure, results in a frequency-dependent relationship. We wanted to look at this same PGE2 data compared to other ultrasound parameters to see if we could find a global relationship that showed a frequency independent relationship. So first we looked at acoustic radiation force and acoustic intensity. And similar to peak negative pressure, we can see that the trend for both 0.5 megahertz and 1.12 megahertz are significantly different, showing that it is frequency dependent. When we plot this against mechanical index, however, we see that the curves for 0.5 megahertz and 1.12 megahertz are not significantly different, and they can be described by a single global relationship. So two things to note here is that, as I said before, we did see an increase in PGE2 at levels beneath that which we could detect the harmonic emission, and mechanical index also takes into account acoustic, is also proportional to acoustic radiation force. However, mechanical index is weighted towards a lower frequency where you have a lower cavitation threshold, which suggests that cavitation may be playing a larger role in driving this response than we had previously thought. So to conclude, we have found that PGE2 is upregulated at peak negative pressures below which that we can detect cavitation thresholds. However, and this could mean that acoustic radiation forces can drive a certain level of PGE2 response, but this is something we are going to look at further. We've also, looking more globally, we were able to see that PGE2 levels were better correlated with mechanical index than acoustic radiation forces. And this suggests that cavitation might be the better ultrasound parameter to adjust when you're trying to optimize pulse focus ultrasound-induced molecular response. For future directions, we are looking to examine PGE2 levels as well as stem cell homing in response to low-pressure focus ultrasound accompanied by a dose of intravenous microbubbles. As I said before, there were no microbubbles used in this experiment. This could allow for better control of the ultrasound bioeffects and could also allow us to better minimize damage when we are looking at future regenerative medical applications. Thank you, and I'll take any questions.
Questions? So, regarding the line of the mechanical index, the graph that you showed, is there any way to correlate this with what you'll get with imaging level ultrasound and microbubbles? Or is this completely different? Because you mentioned there's one of the next steps is evaluating the effect of microbubbles and imaging ultrasound.
I think you could probably correlate it to actual measured harmonic emissions or something similar, but I'm not aware of I do not believe mechanical index would account for adding bubbles as it's a measure of endogenous cavitation.
Well, yeah,
if that answers your question.
The focused ultrasound is at levels much, much greater than what you would get at diagnostic ultrasound. But you know, in regenerative medicine, the downside is that there's always potential for tissue damage. So the idea that the relationship with cavitation exists, we would want to explore going down to something like diagnostic ultrasound intensities and then using microbubbles as the cavitation agents, and that would just give us a lot more refined control over things. Just endogenous cavitation is tough to control, and those bioeffects would be difficult to control with those air pressures. So.
Thank you. Anyone else? Going once, going twice? Thank you.
No, there's one. There's one maybe.
Yeah, so
I'm
not going to ask you a question. Just to comment, with diagnostic imaging, ultrasound, and microbubbles, you can actually stimulate an immune response. In AKI models, the group at
Virginia
UVA actually was able to show that in an ischemic reperfusion injury model in mice, they could actually wind up improving recovery and prevent disease as a result of using diagnostic imaging and bubbles, and by sonicating essentially the kidney and the spleen. So there is a molecular effect that you can develop, and a biological effect you can develop just using diagnostic ultrasound. JCI article in 2014.
Well, next